That's great. Thanks so much, Tobias and Chris and everyone there for the invitation. The series is great, and yeah, I'm looking forward to talking about this paper and also some wider ideas around it and some new stuff that I'm working on as well. So the paper here is called "From the Origins of Meaning: From Pragmatic Control Signals to Semantic Representations," and really it came out of a project that's running at Trinity College, sort of, well, hosted kind of at Trinity College, but has a very broad international group, a big discussion group where we're thinking about the meaning of the concept of representations, thinking about what it has meant, what it means now, what are the usages of it, and what it could mean. And, a lot of that is based around the issue that across different areas, AI, neuroscience, philosophy, people use the term in different ways. It's highly contested, but also end up talking past each other. And that, what we're trying to do is tease those meanings out, but also see how they relate to each other. And that project has been nicely summarized in a piece that was written in the Transmitter by Francis Fallon and some of the other leaders of the group. And so if you're interested, you can see more about it there. And it's really about figuring out what this concept actually means. And so I think that's important work terminologically to do a little bit of brush clearing and hygiene across these fields to help them talk to each other. For me, it's actually deeper than that. I actually think that representations are just fundamentally the bridge concept that we need to connect between brains and minds. And for neuroscience to explain psychology without explaining it away, which is, I think, what's in danger of happening sometimes. And really to let us understand mentality, like what are we talking about when we're talking about thinking and minds and mental causation and things like that. I think we need that concept of representations as a tool to figure out what we mean by that. I don't necessarily take that to be a commitment to symbolic representation or a computational language of thought. We don't have to go all that way necessarily. Just need neural patterns to be about something, at least to get us off the ground. And the traditional way of talking about that, of framing that aboutness, is thinking about representations as being vehicles with content. So some kind of pattern of neural activity that contains meaning or reference to something. And Bill Ramsey has talked about this as a conception that treats the representations as vehicles or representational vehicles as vessels for conveying freight. And he's not saying that in an approving way. And I also find it a difficult framing. It just doesn't sit really well because it makes you think that the meaning of the things is in there somehow. It's being carried by them. And I don't think that's super helpful epistemically or conceptually. So I like to recast them as just meaningful patterns. And that's basically the main thrust of the paper, or at least part of it, where the meaning is not contained in the given neural pattern of activity, it's evoked by it. So it's distributed across the brain in that case. It's relational and it's interpretive. It's not just sitting there by itself, like the meaning of the words that are on the screen here. They're not contained, that meaning is not contained in the words. It's being evoked in your minds by the by your own history and the configuration of your brain, which has tracked and learned those meanings. So it depends on observers, and that necessarily means that meaning is a little bit nebulous. It's a little harder as a concept to get a handle on. You can't quantify it in the way that you can quantify information, and you can't localize it. So, I think people have been a bit afraid of it or a bit allergic to the phrase meaning, but I think it's absolutely just what organisms need to get around in the world. So I'm going to fully embrace it here. Part of the reason I think that sometimes people aren't aren't sure what to make of it is this question of how could the meaning have any causal power in a concrete physical system? Because the meaning seems like it's just abstract and immaterial, right? So how can it matter what a neural pattern, the vehicle of a thought or an idea is about in the system? Isn't all the work already being done by the neural activity? And I think that that's just a mistake, actually. And really, what it's positing is semantic zombies. So it's in a sense, it's thinking, okay, here's how the system works at the level of neural firings and synaptic transmission and ion channels opening and all the rest of that, and we can capture all that activity. So what would the meaning be doing as an optional extra? Like you could sprinkle it in somehow and then see how would that do anything. The causal work is already exhausted by all of the neural syntax in that idea, and I just think that that's um, backwards, really, because for me, semantic zombies are just not plausible. They may be conceivable, but they're not plausible because the meaning is baked into organismal control system just from the get-go. And I mean from the get-go of evolution, of the origin of life. There's already meaningful relations at play within living systems, and it's wired into biochemical circuits of single-celled organisms. You don't need a nervous system for this, but it's also wired into neural circuits of multicellular creatures. So if we think about really, really basically what life is, you can think of it as a self-sustaining pattern of some kind of processes. Like as depicted here, this is a sort of a schematic of like the metabolism of a bacterium, say, a single-celled organism, where all of those processes, all the feedback loops and the interlocking relations between them sustain the whole pattern, right? What's the life is, the liveliness in here is this dynamical regime which the system as a whole entity propagates through time. So the challenge, of course, is that the second law of thermodynamics says it shouldn't do that, right? It says it shouldn't stay organized like that. It should go to equilibrium with the rest of the universe, and living things do their best to prevent that or delay it for as long as possible by taking in energy and doing work to maintain this pattern of processes, this particular regime that is them, that just is what they are. The problem, of course, the challenge for living things is the world doesn't cooperate, right? It keeps changing, partly because of the activity of the organism itself. And so in that case, while the organism has a barrier between it and the world, it still needs to know what's going on out there, right? What's going on out in the world. It needs to get some information that it can act on in order to favor its own persistence in a dynamical, changing world. So to stay alive, then in an uncooperative world, organisms need to know two things: what's out in the world and what should I do about it. And you can think about what's out in the world as just requiring sentience or some kind of sensibility to things in the world, so some sort of sensory systems. And being able to do something about it is basically control systems, so some degree of agency. But there's another element here, which is that you don't want to just be able to do something, you want to be able to do something adaptive, right? So the what should I do part requires knowledge as well, and that requires learning systems. And in the first case, evolution was the first learning system that allowed organisms to, or that equipped organisms with control policies of what's a good thing to do given certain circumstances in the world. Of course, later on, it equipped them with their own learning systems where they could do on-board learning in real time over their individual lifetimes. Now, if we're thinking about those control policies, the interesting thing is that nature solved these questions in reverse order. You would think an organism would have to know what's going on out there to identify things in the world and then figure out what should I do about it. But that's not the way it happened. What happened first was just configuring policies. What should you do about it without knowing what's going on out there, without representing internally what's going on out there? So here's an example. This is our little bacterium. Now there's some stuff in the world. There's dangerous things. There's food that are relevant to it because it has a purpose to stay alive. And that purpose is tautological at this stage, in the sense that things that are good at staying alive will stay alive. So there's a selection for the patterns that have these kind of control policies that turn out to be adaptive in the world. So there's absolutely a circularity to this, but it's still absolutely reasonable in my view to call that purpose, even though the organism's not, of course, aware of it. But what that means is that now things in the world that it can detect with these little receptors on the surface of its membrane there, it can get information about things in the world that have a value relative to that goal of persisting, right? It's good to go towards food. It's good to move away from dangerous things. And the meaning of those signals internally can now be apprehended as approach or avoid, right? There's an imperative kind of a signal at play there. So, well, one thing to say about this is that this is a new kind of causation that just didn't exist in the world before living things. There was no informational causation before living things. This is not, there's no physical energy or matter being transferred across the membrane here. There's just detection of a signal, a little wiggle inside, the conformational change inside the membrane of the cell that transmits a signal that is acted on by the organism, and evolution says whether it was a good thing to do or not. So I take this to be really the origins of meaning. Those signals mean something for the organism. They're physically correlated with something in the environment, and they have value relative to this aim of persistence, and they're used to mount an adaptive response. So you can think about those as these very simple pragmatic couplings in an isolated sense. If A, then do X, right? There's just a single, in this case, a single stimulus being detected and a single response like a reflex being executed. And again, the important thing is that these signals are not first decoded and then acted upon. They're just acted upon. The organism doesn't know what's out there. It just acts in this case. These signals are imperative. They're not indicative, not yet. They're not representational, but they're still meaningful, I think, or at least I would argue that's a reasonable way to frame it. And the meaning here, I just wrote this today, is extensive, and I don't know if that's the right word, um, but it's extended through this loop between the world and the organism, the action that the organism takes, the outcome, right, the consequence of that, and whether the world says it's a good thing or not. All of that is where the meaning inheres, I think. So it's relational and it's grounded through action and these consequences, but it's diachronic, right? So this loop iterates over and over again, and that's how the meaning, that's how the policies become instantiated in this case, the biochemistry of the organism, but the same logic applies to neural circuits that may be innately wired to embody control policies for environmental signals. Now, these things don't have to be so simple, right? And they rarely are, because organisms rarely face stimuli one at a time, right? The world is throwing all kinds of stuff at them, so they often need some contextual control. They need some second order policies where you can see here, an organism is actually integrating a number of signals at once and then doing X. That may be configured in this kind of a way. So there's more flexibility available here with some limits of what can be accomplished, right? But pragmatic couplings are just sort of in a cybernetic sense quite effective, right? I mean, this is how control theory works. This is how control systems are built. And the benefit here is that effectively what's happening is that the organism as a whole is assessing a situation as a whole and deciding, all things considered, what's the best thing to do. It's just that it works through that by these sets of pragmatic couplings that are intercoupled now. But it's not just responding to isolated stimuli in a stimulus response kind of way. And you can see that kind of thing in neural systems. This is a figure from a paper by Paul Chisek looking at the lamprey system. So lamprey have these primitive fish that have pretty simple visual systems, and they will avoid a looming object at the side, and they'll move towards a little object sort of in the front of them. And those things are just wired pragmatically into the circuits that go from the retina to the tectum to the motor control centers. These are hardwired approach or avoid things, but there's also second order control, because if there's multiple looming signals, then what you want to do is average them and take an escape response between them. Whereas if there's multiple signals that could be prey, then you want to choose between them. So there's a different kind of system for integrating. This one is competition, this one is summation. And you can think again in a control system way how to build up that kind of architecture. So those control policies are great. They get organisms off the ground with adaptive behavior, but they're not very flexible and they're not very scalable. And the reason is that there's a limit to how many higher order contextual policies you can put in, or interactions you can put into the system at a single level, right? If you're doing everything at a single control level, then you have limits on how many things you can handle, basically. And that means that at some stage, if organisms want to be able to do complex behavior flexibly in novel scenarios, then they're going to need some internal representation, especially under these conditions when additional processing is required to infer the source of the sensory data, when you're not just responding to a signal, but you have to figure out what caused the signal, when information about multiple factors has to be integrated in novel ways, right? Not just in ways that evolution could pre-configure a contextual policy for, and when information must be borne in mind over time, which can happen when you need to integrate it with other things. And especially because a lot of behaviors are not just momentary, they're the behavior itself is extended over time. So if you think about a creature like a nematode worm here, they have kind of simple cognition. They're integrating some different sources of information, but they're not thinking about much because they can't be much on their mind, as it were, because they don't have access to much, right? They respond to chemicals and to direct touch. That's all they have: olfaction, and they have mechanosensation, but they don't have any other senses. So they really inhabit the here and now. The things they're responding to are right next to them, and the stimuli that they're getting are the things that they're interested in. They're interested in molecules in the environment. They're interested in things that are touching them, right, immediately and very proximally. And that's not true for organisms that have developed long-range senses. So things like vision and hearing, where we're taking in sensory data, which is, vibrations of the air or water or refractions of electromagnetic waves, the wavelengths of photons that are hitting our retina, but we're not interested in those things. We're interested in what caused them, right? We're interested in what is it out in the world that those photons bounced off of before they entered my eye. And that means that there's a level of things that we care about that should be the things that we think about. We don't want to think about our photons that we're collecting, right? We want to think about the inferences that we make about the sources of the sensory data. And that requires a lot of internal processing. So that processing happens in this kind of hierarchical way where as you go from one level to the next, it's not like this situation on the left where, if there was just one neuron at a time, you would inevitably just lose information because of just loss and noise. Instead, it's like the system on the right where there's convergence at each stage, where meaning is now being extracted or in a sense created as these levels of processing happen. It's not available out in the world. It's not available, for example, just in the pattern of activity of the photoreceptors, because the photoreceptors don't know whether their neighbors are active, right? The retinal ganglion cells that integrate across them, they know what the patterns are across the visual field in relation to other retinal ganglion cells and so on, right? So they're doing work to detect features and to report that, right? There's already internal representations at the stage of the retina, and that just continues extracting more and more higher order information as you go through the visual system, from lines and edges and features up to types of objects like faces or houses or scenes and so on. And those have to be represented. It's not optional there's no direct perception of a face. That's an inference that the organism has to make using that kind of a system. So now we've really moved from pragmatic couplings to internal representations that have some meaning. They're about something out in the world, and they've emerged through this extraction of higher order features, and they can be reported to multiple systems. So now we're, instead of just being at the level where it's if A, do X, or even this kind of contextual control, now it's if A, report A, and then that's used by the system to inform action later on. And it can be combined with representations of its current states and goals, and so on. So these perceptual representations are the output of the organism making sense of the world, right? Or this is how it makes sense of the world. They're inferences. And I think you could call them beliefs, not in a psychological sense, not in the high level psychological sense necessarily, but in a sense that they're reported, the report about something in the world, and it can be wrong, right? This system can be mistaken in those inferences. But that's what they're for, right? They stand in exploitable relation to things in the world or in the state of the organism. And to use Nick Shea's terminology, they're about something, and the meaning is grounded by experience, and by a web of context, as I'll talk about. And they're also for something. Even though they're decoupled from obligate action, they're still used to inform action. So this idea of grounding, of course, has been one of the bugbears of the theme of the topic of representations. And I think if you start with the idea of direct sensory motor couplings, and then where already the meaning is just grounded by feedback from natural selection with respect to the aim of persistence, right? You've got something in the world directly perceived and acted upon, and then natural selection says that whether that was a good thing or not, right? But if you just add intervening layers between the sensors and the motors, well, you're still eventually grounded at the edges. You've just now got some internal kind of economy of representations that's at play. And you can create new types of meaning at each level that you go through, higher order, more abstract meaning, more integrative kind of meaning. But it's still grounded by correlation with things in the world and through the consequences for action. So, sometimes people say, well, the things that we're thinking about, we don't know that that reflects anything in the world. We have this kind of, idealism. And, the simple kind of rejoinder to that is, well, natural selection is testing all the time whether your internal representations match things in the world. And if they didn't, then we wouldn't have these systems and you wouldn't be alive. So there's a grounding that just comes from the need for these consequences to be good, basically. That grounding too is built up. It's not all of it doesn't appear all at once. It appears through active exploration and cross calibration. So when a baby sees something and then it picks it up, then it's learning things that look like that feel like this, and they weigh this much, and they taste like this, and they're hard or they're soft or whatever. So there's learning of the properties and the associations between them through this active sensory motor exploration that keeps everything grounded and starts simple, but can be scaffolded on to build much more complicated cognitive kind of level representations. So this is a quote from Gualtiero Piccinini, which is basically very much along the same lines of thinking of these as situated, action-oriented representation. So he says neural representations emerge diachronically through the dynamical interaction between neurocognitive systems, their body, and the environment. And they depend on such a dynamic interaction for their existence and updating, because of course those representations are not fixed; they're updated all the time. So we moved from these couplings to these ones, which are grounded through that kind of sensory motor history, and that means that they're linked to prior knowledge. So all of that history is basically building up a world model, a model of the organism in the world, a model of what the organism can do in the world, a model of the properties of things, a model of the way that events normally go, of contingencies between A happening and then B tends to happen, and so on. So we're developing categories and schemas and maps of these kinds of contingencies, and through all of that, figuring out the causal relations and the affordances in the world that allow us to get around in the world, allow any organism to get around in the world by constructing a self model and a world model and a self in the world model. Basically, those two things are not. I shouldn't really actually have them pulled apart. They're so entangled that everything about our perception is based on what we can do in the world afterwards. So what I would say is that the meaning now is very, very relational. It's very distributed, right? It inheres in the web of relations that are activated by a particular kind of set of inputs, or an inference, like an inference that there's a face in the world, and recognition of whose face it is will activate a schema of that person. And that will draw up, the thoughts of all of everything that you know about them that's embodied in the context of the nervous system and everything you've built up. So we can think about this, the particular pattern as part of a representational system. We don't have to reify representations as objects. We can have the system doing representational work in a kind of a structuralist sense, where one part of the meaning of any given pattern that you see is that it's not all the other patterns that could have been activated. And the other aspect here, so that's the first sort of aspect of the relational structural encoding here, but also there's this idea of activating these relational schemas where importantly, the meaning is not encoded by one set of neurons and then decoded by another. That's not what's happening in the nervous system. These neural patterns, I think you can think of as semantic pointers, to use Chris Eliasmith's term, I believe, where, if I say the word bird or dog or car, Well, all of those will activate stored knowledge of their properties and their causal relations because they're pointing at various things like has feathers, can fly, has a beak, can be eaten, all of those kinds of things. And in thought, then those activation of those patterns can fill conceptual roles by pointing to all of those things and uh, in a sentence, what you're thinking about being the thing that I'm looking at, or the thing that I'm petting, or the thing that I'm driving, those can be all the conceptual roles that can be filled. So you can do conceptual work with these concepts where all of the meaning doesn't have to inhere in the little neural pattern that activates the concept. And I think there's a an interesting analogy here. So this slide is entitled Inactive Structuralism, where you can think about LLMs that have a web of relations between concepts, but they have a world model, but it's a world of words model, right? It doesn't actually make contact with the world itself. It's totally self-contained, but it's excellent for reasoning over all kinds of concepts. And I think you can take that sort of structuralist view and ground it by just making it inactive. So you just extend those relations out into the world and back again, and then you get a much less sort of problematic kind of structuralism. Now, there's a question. What time is it? I'm doing okay. Um, I'm arguing, I have been arguing, that the meaning of these neural patterns is important, right? That a semantic zombie is implausible and actually sort of inconceivable. It's just not the way that things work. But there's a challenge, of course, where we could say, well, actually, doesn't the neural syntax really do all the causal work? That's where the physical oomph is in the system. Why are you talking about meaning? How would we know that the meaning is important? How could you actually distinguish that when it's always riding on some pattern of neural activity? And this is a topic that myself and my student Henry Potter dealt with in another paper called Beyond Mechanism, Extending Our Concepts of Causation in Neuroscience, where we really argued that actually the causation in neuroscience has to be thought of diachronically, and it has to be thought of as embracing other kinds of causation from just production causes, right? So a lot of people think of causes as just physical forces, as if the only thing that's important in what happens in a system is the oomph that gets delivered by production causes. But dependence causes are just as important. And in the nervous system, we know that that's the case because basically each neuron or each population of neurons is a black box to the other neurons that are monitoring it, right? And so what you have is you got noise at multiple levels. The details of neural firing are not reliable. Each neuron is a black box to the next neuron. And actually, a lot of those low level details are lost in synaptic transmission. A lot of action potentials don't result in a synaptic fire release, right? A lot of release of transmitter doesn't result in an action potential. There's a lot of filtering and integration that goes on at individual neuron level and at population levels. And the meaning the causation is really multiply realizable. And I think this is really the important thing. We can ask, where is the causal sensitivity in the system? At what level? Is it at the level of the details of neural firings, or is it at the level of the patterns of neural firings at a coarse grain kind of a sense level? And that's where the meaning inheres, right? That's why there's causal sensitivity at that level. And that's what I want to argue is that what matters is what the patterns mean. So I think a typical way of thinking about causation in the nervous system is this driving view. You've got neuron A becomes active and it drives downstream neurons. And that is it's a view that's easy to fall into, especially because you can stick electrodes in neurons and you can zap them, and it does cause cascades of electrical activity, right? And eventually they might even cause behaviors. But I think it's fully ass backwards. I think that's exactly the wrong way to think about what's happening in the nervous system. In fact, the active elements, the ones that are doing work here, are the downstream neurons. They're doing interpretive work based on the configuration of their system, their synapses, that embodies criteria for what they're interested in, right? If the incoming pattern doesn't match what this neuron is looking for, it's not going to fire. So when this neuron fires, it's sending a signal that's not just a decoding of the signal it got here, it's an interpretation of all of its signals according to some criteria that have been historically configured that mean something. And now when B fires, the rest of the neurons downstream interpret that meaning. That's what they're looking for. So, like every single cell, this neuron is interested in what's going on out there and what should I do about it. It just has a slightly different array of sensory apparatus that it makes this decision with. And this relates to what Peter Tse has called criterial causation, which I think is a good way of thinking about it, where a neuron's firing depends on its inputs. That's absolutely true. It does need some of that electrical activity and the chemical signals to impinge on it, but it also depends on the way that it's configured. And that configuration encodes criteria for firing. It encodes meaningful criteria that set the sensitivity of the neuron to specific aspects of its inputs. And those criteria reflect the past history and the current state and top-down constraints and neuromodulation. And all of those things can be tweaked on the time scale of real behavioral activity. And so there's real-time modulation of those criteria through various means of synaptic plasticity, as well as the much longer term configurational kind of plasticity. So another way of thinking about causation or testing our ideas of it is with a counterfactual, right? We can say if A is identified as the cause of X, then we expect if A is the case, then X will happen. But we also expect if A is not the case, then X should not happen. Right? So if we're saying that A is the cause, then that counterfactual should hold true. So in this case, if A is taken to be a particular neural pattern of firing, where all of the details are really important, then what you'll find is, yeah, some particular pattern might drive activity of downstream neurons, but another pattern where it's not A, now it's something else, could also drive those things. So the counterfactual doesn't hold at the level of the details of neural syntax. It holds at the level of neural semantics, the patterns that mean something in the system where the meaning just is the configuration of the system and the interpretive work that it's doing. The equivalence classes that neurons are paying attention to make the meaning of the state. So we can think of, for example, one population of neurons that's monitoring another one, where this population of neurons could be in multiple microstates. But what this population cares about is whether the microstates fall into what it recognizes as pattern A or pattern B. And it doesn't care about the minor arbitrary sort of details that can shift over time, they can drift over time, and they're really multiply instantiated here. So what you can have is a kind of causation here where it's absolutely dependent on the pattern, and pattern A means something, which is adopt state X, and pattern B means adopt state Y. And that's exactly the kind of system dynamic that we see in real neural systems, where you can see these communication subspaces between different areas where patterns of neural activity in one area may be actually sent to multiple areas, right? That can be broadcast to multiple downstream consumers who are maybe interested in different things and may respond differentially depending on what pattern their this population of neurons is in. So that sort of differential sensitivity to population-based patterns is exactly the way that the neural system seems to actually work. And what this means for, thinking about eliminative reductionism, where, some people would say, well, all of these things that we're talking about in psychology, mental states and beliefs and so on, and processes of decision making and making choices that you call cognitive are actually nothing more than these neural activity patterns playing out through the system, its computations and brain states. But really, neuroscience is the right level to think about that. And if you want to keep being reductive, you can go down to atoms obeying deterministic laws. But actually, I think that's also fully ass backwards. I think that in fact, the neural activity patterns and the computations that are happening are instantiated in the way that they are because of the history of what these things mean. The neural syntax has its causal power in the system solely by virtue of the meaning of the patterns that it entails or evokes. So in that sense, we can't just think of cognition as some sort of epiphenomenon that it's nice to talk about. It's a convenient way of talking, but it's not where the real causal work is being done. I think that's absolutely not the right way of thinking about it. The cognition is based on the meaning of the neural patterns. It depends on, it supervenes on some neural patterns, but the details are not important. What's important is these elements of cognition, which are rightly called beliefs and emotions and desires and goals. Those really are the things that are on our mind. And just one final thought then, coming back to this issue of how could mental um, content, right? How could the meaning of a thought, say, have any causal power in the system? I think we can think of that in a few ways. There's the problem of dualism where, thoughts are sort of immaterial, but then you have this classic problem of, okay, how do they then feed back down onto the physical system? That seems to be a problem in this dualistic way of thinking. And you can have reductive materialism where you can say, okay, yeah, some pattern of neural activity does lead to a feeling of a thought, some kind of experience, but that has no causal power. It's just an epiphenomenon. It just floats up there. It feels like something. What's really important is the neural syntax doing all the work down here. And I think there's another way of thinking about it, which I'm kind of call cognitive realism, where the neural patterns mean something. It could mean A, or the white pattern could mean B. And depending on which pattern is active and it meaning A or B, that determines whether these neurons respond to it or how different neurons respond to it. That just is what's happening there. So I would argue that semantic causation is not mysterious. It's not a mystery as how the meaning could have causal power in a physical system. Semantic properties just are causal properties. That's what they are. What a pattern means is the effects it evokes. And once you exhaust all of those, you've exhausted everything it means for it to mean what it means. And all of that, of course, depends on configuration and historicity. And so it has to be thought of diachronically, right? You can't just think of causation synchronically. So finally, then, I would argue that the brain is a semantic engine, that it runs on meaningful patterns of neural activity, and we call some of those representations. And they're grounded evolutionarily and ontogenetically through actions and their consequences. So no zombies allowed. And yeah, that's it. I'm going to end there. Thank you for your attention. And here are some related works. Some of these ideas were already discussed in like 2023 book Free Agents, but there's a bunch of new papers, many of them with Henry Potter, who has graduated and now doing a postdoc in the US. So thanks very much, and I'm happy to have a discussion.